Okay, so today we're going to do lesson 2 in, lesson 3, lesson 3 in chapter 11. We did lesson 1 before I left, which remember was gases, and we talked about how they didn't have any intermolecular forces between them. And then we talked about, well, what is a molecular force? And for that, we did notes yesterday on intermolecular forces, the 3 different types of intermolecular forces. And the 3 types were dispersion, which was by the dispersion forces, which was from the electron cloud shifting. And these were temporary and weak unless you had a bigger molecule. So on this, you'll note that, I think we talked about this yesterday, that bromine is a liquid and hydrogen is a gas, and that's because bromine is larger and has more electrons in its electron cloud, but both of them have only dispersion. Then we talked about dipole-dipole, which were molecules between, which were forces that are between permanent dipoles. And the permanent dipoles are made by the positive and negative charges. And the example I gave was sodium chloride. In smaller molecules, this is a stronger force, but as the molecules get larger, the dispersion forces kind of overtake because of the size of the electron cloud. Now, the third one we talked about was hydrogen bonds. I made a point of saying they are not bonds, they're actually intermolecular forces, and they form a dipole-dipole because of the positive and negative that's super strong, because what the hydrogen is attached to is fluorine, oxygen, or nitrogen. And these 3 elements are highly electronegative, and so they really pull those electrons toward them. They create this large negative charge on the oxygen and then a large positive charge on the hydrogen, which are strongly attracted to each other. Okay. So today we're going to talk about how these intermolecular forces affect liquids and solids. So we're going to start with liquids because we know that they have no effect on gases, and that's why the gases act independently, those particles. But with liquids have more particles per volume. So density, we're going to use the term for density, we're going to talk about particles per volume. That's how we're going to define it, okay? So liquids have a higher density than gases. And they can be compressed. And the reason that they can be compressed, as opposed to, we talked about solids cannot be, but liquids can be only slightly compressed. And that's because there's a little bit of room in between those particles. So with a lot of pressure, you could squish those particles together just a little bit more. Now, these particles, they move around a bit. But not like gases. Okay, now liquids are fluid, and the definition of fluid is that the particles can flow, and they also have the ability to diffuse. Now, are gases fluid? Yes, gases are also fluid. Gases are also fluid. They have the ability to flow or diffuse, and so that makes them fluid. So both gases and liquids are fluid. Now, liquids can diffuse through another liquid. So they can go through those particles just like gases can, but more slowly than a gas. And the reason is because intermolecular forces. And interactions cause those particles to have more resistance to moving between each other than with gases. And remember, liquids have stronger IMFs than gases. Now, there's another term that we use when we're talking about fluidity. We talk about something called viscosity. And viscosity is the resistance to flow. So why does one liquid, why is the texture of it really thick, like honey or like syrup, but other liquids like water or alcohol, rubbing alcohol, they have very little resistance to flow. They just go, right? So why is that? Well, so they have greater intermolecular forces and so greater viscosity. So in the example that we're going to put here is syrup and honey versus water or rubbing alcohol. Okay, and so both of those have lower intermolecular forces than liquids. Yes, I mean, we've talked about how water has high intermolecular forces, but compared to a viscous liquid, it would have a lower intermolecular forces. Now, what happens with these intermolecular forces is that if you increase the temperature, you're going to lower the viscosity. And the reason is it overcomes those intermolecular forces. So by raising the temperature, you can make honey less viscous. By raising the temperature, you can make syrup less viscous because you start to break apart those intermolecular forces. Does that mean that it breaks down into carbon and hydrogen and oxygen? No, it does not. Those intra bonds stay together. Only the forces between the particles are overcome when you raise the temperature. Now, surface tension is the measure of the inward pull of the particles. Now, surface tension is like why insects can walk on water, right? Why bugs can walk on water. And the reason is because those hydrogen bonds between those water particles are strong enough that they can stretch a little bit. There's like a little bit of pull toward the center of them, so they hold on to each other and they pull, setting up a little bit of a trampoline for those insects that they can walk on the water, and it's soft and it's a little bouncy. Now, capillary action is something that is seen when we look at the meniscus in a narrow tube. So let's say we're looking at a graduated cylinder, okay? And it has, I'm going to draw a really big meniscus here. It has a meniscus that looks like that, okay? So this is all the liquid here, all liquid. Okay, so this part here, where the water attaches to the glass, this is called adhesion. Adhesion. So adhesion is the attraction between molecules that are different, so the water and the glass. Whereas this part here, the fact that this makes this dip as opposed to just falling off is called cohesion. Okay, so cohesion is where the particles hold on to each other, identical molecules. right? And adhesion is between different molecules. All right? So cohesion, and then in red, adhesion, and we'll do this, molecules that are different. All right? Okay. And so next we're going to move on to solids. Solids have a greater density, a higher density than liquids. And remember, when we're talking about density here, we're talking about particles per volume. All right, and that's due to even greater intermolecular forces. So the particles are not fluid. They cannot move around. They cannot pass between each other. They're stuck in their fixed space, and they have very strong IMFs. Which make it so that those particles can't move. The other thing is the density of the particles of solids can't be changed. It's the highest density of gases, liquids, and solids. So in other words, you can't compress them because that would push more particles into one space, and you can't expand them because that would lower the density. So the density of solids can't be changed. That's one of the criteria that we define actually for solids. Now, there are 5 different types of solids, so we're going to go over them very quickly, all right? So the first, there are 5 different types of, there's 4 different types of crystalline solid. There's actually 5, but we're only going to cover 4. So 4 types of crystalline solids, okay? 4 types, that's not types. That looks like typo. Types. 4 types of crystalline solids. Now, in a crystalline solids, the atoms are all arranged in this orderly pattern, this orderly geometric pattern, and they're pulled together because of the 3-dimensional structure. So it's not just like random. They're actually put into this lattice structure where they make up, in many cases, they make up this cubic structure in many cases, not all, but in some, but just so you're getting an idea of what we're talking about. They make up this cubic structure, right, where all the particles are in a cube. And the smallest cell of this is called a formula unit. So you've heard me use that term. So these crystalline structures are polar and they have dipoles, and that's why they form this structure. Now, a molecular solid is not usually liquid at room temperature. So this would be like butter as opposed to olive oil, right? And it's a molecular solid. It's not liquid at room temperature except those. Oh, well, this didn't work out. Sorry. Go back. Solid. They're not usually solid at room temperature except those with largest masses. So the ones with larger masses are solid. Again, we go back to those dispersion forces, and that's things like sugars and some fats. So like butter has a very, very, very large mass to it. Whereas something like olive oil has a smaller mass. And so because of that, the dispersion forces in olive oil are weaker. So they are held together by, molecular solids are held together by dispersion forces and hydrogen bonds. So both of these are included, and they're very poor conductors of electricity and heat. mostly because they have no polarity to them. And so if those molecules have no polarity, they certainly can't pass electricity through them with a positive and a negative charge. That wouldn't work. So that's number one. Number two is ionic solids. And ionic solids are solids like NaCl, where there's ions, or KBr, where there's ions. So those positive and negative ions are attracted to each other. So each ion is surrounded by ions of the opposite charge. They have very high intra and intermolecular forces. And that's what gives these compounds like a hardness and high melting point. So for example, sodium chloride melts at 2500 degrees Celsius, very high, right? And that's because it has really strong intermolecular forces, right? And separating it has to be done chemically because pulling them apart would take a lot of force. These ionic solids are very strong, but they're brittle. And they shatter because their bonds are very brittle. Number three is metallic solids. And metallic solids are made of positive metal ions. Most of the time, these are transition metals. Transition metal cations, which are positive, right? Because they have the D sublevel. And that D sublevel allows them to have what we call a sea of electrons. And that sea of electrons, like that D sublevel, allows for all kinds of physical properties. So for example, and the reason is because those electrons act like, the word actually is like, I can't remember, right? Physical properties, they act like wheels or balls between plates where you can slide. They allow the metals to slide back and forth across on top of each other. And by doing that, they allow for things like color. That's why we have copper that's colored kind of orange versus silver, which has that silver color. They have different densities because those particles have the ability to slide. They also are malleable and ductile. Now, both of these, malleable and ductile, malleable means squishable, very technical term, and ductile means pull into a wire, so you can pull it into a wire. Now, those are unique characteristics because you're not pulling apart the atoms or the molecules, you're actually sliding them over these ball bearings, over these balls of electrons, which allow the particles to slide back and forth. And so the mobile electrons make these metals good conductors. Of heat and electricity. Okay, all right. Number four, amorphous solids. So in an amorphous solid, so we have molecular, we have ionic, we have metallic, and now we have amorphous. The particles are not arranged in a specific manner. Pattern. The reason is because they are melted material that hardened too quickly for the crystals to form. So the crystals didn't have time to line up and get into that pretty crystallized form that you see, like with salt or with sugar, where they're tiny little squares. The amorphous solids don't have a chance to do that, and so as a result of that, through science, you get glass and rubber, both of which are amorphous, and they are solid, so their particles don't move, but they're not in this distinct structure. Okay, now down at the bottom, that seems like a lot of flashcards to me. I'm just saying, a lot of flashcards. Down at the bottom, the phase changes. For the vocabulary, we're going to add a few so to make up our list. So we're going to add dispersion forces, we're going to add dipole, which are London dispersion forces. We're going to add dipole-dipole. We're going to add hydrogen bonds. We're going to add over here viscosity, temperature, diffusion. We're going to add boiling point, melting point, freezing point, and point, okay, and I think that's it. That should be 20. Let's see, 5, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 words. 20 words, okay? And then that's on Thursday. That's on Thursday. And then on Thursday, we're going to do the vocab quiz, and then we're going to do phase changes. And then all we have left to do is graphs, and we have a lab for this unit. Okay, great. Talk to you later. Bye.